In this video, I'm going to continue the description of the four-layer internet model, and I'm going to be particularly telling you about two different transport layer services. One of them is TCP and the other is UDP. Both of these are very widely used throughout the internet. I'm going to start with TCP. TCP is an example of the transport layer. When an application calls TCP, it's going to hand it some bytes that it wants delivered to the other end. TCP is going to place these bytes into a TCP segment, add a header, and then it's going to take over from there and deliver it to the other end. So returning to our four-layer model, we can think of the responsibility of TCP, or the transport layer, to deliver those packets to its peer at the other end, or deliver the bytes on behalf of the application. So it's really taking bytes from here, delivering them across to the transport layer and up to the application at the other end. That's the service that it's providing. And we'll look at it in a little bit more detail in a moment. So let's take a look at some of the properties of TCP. It has the following main characteristics. So first of all, remember that the network layer, the layer that sits below, provides no guarantees that packets will be delivered in sequence, or even that they'll be delivered at all. So TCP sits on top of IP and provides a reliable service so that the application can rest assured that if it's at all possible to deliver data to the other end, TCP is going to take care of it. So here are the main properties. The first one is that TCP provides a stream of bytes service. So this stream of bytes means it's going to deliver the bytes that are handed to it by the application to the other end, and it's going to provide them in order. TCP is connection-oriented. Connection-oriented means it's going to start by establishing some state at both ends so that it can keep track of the communication. And it's going to do this through a three-way handshake that we're going to take a look at in a minute. Perhaps most importantly of all, TCP provides reliable delivery, and it uses a number of mechanisms to do this. First of all, it's going to use acknowledgements to indicate that delivery was received at the other end. So the receiver is going to send acknowledgements back to the sender. It uses checksums to detect if data was corrupted along the way. It's going to use sequence numbers to detect any data that was missing. And it's going to use flow control to prevent overrunning the receiver. And we're going to see all of these sometime soon. The next property that TCP provides is it's going to deliver the bytes in sequence at the other end. That means that the data, the bytes that are delivered to the application, will be delivered in the sequence that they were transmitted. So it's going to use those sequence numbers for this as well. Finally, TCP helps to prevent network congestion. It's not really part of the TCP service model, but it's an important characteristic of TCP, and we're going to see whole lectures about this property later in the course. TCP provides what we call a stream of byte service. What this means is the application will hand bytes, as many bytes as it wants, down to the TCP layer, and then TCP is responsible for delivering those to the other end. So for example, if the server shown here is A, if an application running on that server has bytes to send, and let's say the first 80 bytes here, or the first 81 bytes, these are going to be delivered by TCP to the other end. That's its job, that's its responsibility. It's going to take care of delivering them from end to end. The delay here, of course, is the end-to-end delay of the first packet getting from A to B. TCP doesn't deliver these in individual bytes, of course. It's going to use segments. So TCP is going to collect together a set of bytes. Let's say it takes these first bytes from 0 to 80, puts them into a segment. This is the data portion of that TCP segment. It'll add a TCP header, and we'll see what that information is in a minute, but it's essentially to tell B at the other end what to do with this data when it receives it. That is then placed into an IP datagram, so it's encapsulated into an IP datagram, sent across to the other end, where it will appear to the TCP layer at the other end as a TCP segment, hopefully the same one that we sent, and so that will find its way across to the other end. It will then extract those bytes from 0 to 80 and hand them to the application. So as far as the applications at A and B are concerned, they just see a stream of bytes from one end to the other. You might be wondering, how many bytes can we place into the data portion? Well, it could be as few as one, or as little as one. If we have a byte that needs to urgently be sent, it can be placed into that data portion and then sent immediately. At the other extreme, we can send up to the maximum amount that IP will allow. And there is a property of the network called the MSS, the maximum segment size, which is the maximum amount of data we're allowed to put into an IP datagram. And that's a property of the network link. So that data segment can then be sent when the segment is full, or when TCP times out waiting for the application to send it new data, or it can be deliberately pushed if there's an urgent need to send the data quickly. This is the TCP segment format. At the top I show a IP datagram. This is the header, this is the data portion, and we can see this TCP segment sitting inside it that's been encapsulated. And I've exploded the view of the header here so we can see the entire TCP header. Let's look at what some of these fields are, because it helps us understand what TCP is doing. I would never expect you to remember what this format is. I want you to understand what the main fields are and what their purpose is. So the first one is the destination port. The destination port tells us which service we want this stream of bytes to be delivered to at the other end. I'll explain that in a bit more detail in a moment. Similarly, we tell it the port number that was used by the sender, and this is going to help any returned bytes, any ones that are sent back from the application at the other end, find their way back to the correct application at the sender. We need a sequence number, and this is a sequence number representing that byte, the first byte in the data portion. So this would be the first byte down here in the data portion of the TCP segment. And it tells us its sequence number in that stream of bytes. Because TCP provides a reliable service, there are acknowledgements are sent back. And so an acknowledgement will include a sequence number telling A, which bytes have been correctly received. And the way that the receiver, B, does this is it sends an acknowledgement back indicating the next byte that it's expecting to receive. This tells it that it has successfully received all the bytes up until that one. Next field is a checksum, and the checksum is calculated over the entire data and header. So all of the TCP segment is used to calculate the checksum. And this helps us to check that the data is correct. So when it's received by the application, it knows that any retransmissions have taken place and that the data is intact. There are a bunch of other header fields that help implement the service overall, including a bunch of flags for things like indicating this carries an acknowledgement, or that this particular one is urgent and needs to be pushed, or that we want to reset the TCP connection. We'll worry about those a little bit later, and they're a not so important part of the service overall. We say that TCP is connection-oriented, which means that before communication takes place, there is a handshake to establish the state at both ends in order for the arriving bytes to be correctly delivered to the right application and for any retransmissions to be taken care of. So I'm going to show these as vertical bars between the client and server with time progressing down the page here. So this will be time moving in this direction, and we're going to look at how this progresses. So first of all, the client is going to send to the server when the connection is established. It sends what we call a SYN. SYN is short for synchronization. And this is a special segment that has the SYN flag set that tells the server that we're establishing a communication. The server will respond by acknowledging that it received that. It will also ask for it to establish a communication in the opposite direction. Why does it do that? Well, TCP is actually establishing a stream of bytes in both directions, from the client to the server and from the server back to the client. So we can think of it as two dependent streams of bytes. They're dependent in the sense that The stream of bytes carrying in one direction are carried in segments that carry acknowledgements for the other direction. That way we can piggyback the acknowledgements on the segments going in the opposite direction. Okay, so once the server has sent the SYN plus ACK to indicate that it acknowledges the establishment in one direction and asks for a connection in the opposite direction, the client sends back an ACK. So it's SYN plus ACK, ACK. Now we've both established and acknowledged in both directions, and now we're ready to go. TCP is so important to the internet, and the three-way handshake is so important to TCP. Hey, it even makes a great fashion statement. Finally, at the end of the communication, after the data has been transferred, there is a close down or a tear down. This actually happens in a slightly different way. Instead of being three-way, it's four-way, because we can close down each direction independently. So imagine the situation where A has sent data to B and has finished sending its data, even though B hasn't finished sending data back to A. A can close down its connection from A to B, and B will then close down its when it's ready. This is how it works. So the client might send what's called a FIN message, that is a TCP segment with a FIN flag marked, to indicate that it is finished. The server can keep sending data back because it hasn't closed down its stream of bytes in the reverse direction. But it will set the ACK flag to indicate that it's acknowledging the close down by the client. Finally, at some time later, when the server is ready and it's finished sending its data, it will send a FIN, and then finally the client will ACK that. The port numbers in the TCP header are used to identify the service that is being requested at the destination. They're used to demultiplex the segments as they arrive at the destination so they can be delivered to the correct user process. So let's take a look at an example of this. Imagine A, so this is server A over here. It has two user processes running, two applications, the web client and a mail client. Imagine that A is sending an HTTP request to a web server running on B. How does that happen? Well, that stream of bytes coming from the client will be placed in a TCP segment. So there's the TCP segment that will then be encapsulated into the IP datagram. So I'll draw the TCP header and then the IP datagram that is going to contain the encapsulated TCP segment that's going to be sent across to the other end. When it's received at the other end, the TCP segment is taken out. So here is the TCP segment that's been removed. We now have to decide at B which of the applications it's going to be delivered to. And the way that it does this is by looking at the port number. There are well-known port numbers representing specific applications. So for example, you may have seen this before for HTTP, which is the protocol that's used by the World Wide Web. That particular port number is 80. In other words, the port number that's used for the destination port number will be 80, and when the segment is reached at the other end and it sees destination port equals 80, it will then take out those bytes and send them up to the web server at B. If instead there'd been a port number that's reserved for the mail server, then the bytes would have been delivered to the mail server at the other end. So you can see that the port numbers are serving as a means to demultiplex the traffic to the correct application at the far end. You can easily find a list of the port numbers, the well-known port numbers, on Wikipedia or on a textbook if you're interested. The sender also sends a port number, which is the source port number. And this is used for the segments that come back in the opposite direction, so that, for example, when the web server was to respond and the segment is to be received at the other end, whatever the port number was that is used by by A when it was sending the original segment, and that's one that it just generates randomly, that is used to then deliver the correct bytes up to the application process. So, source port, destination port, both used for demultiplexing the data into the correct application at the far end. That's all I'm going to say about the TCP service model for now. I'm going to move on to the UDP service model. The User Datagram Protocol, or UDP, provides a much simpler service than TCP. It basically provides a connectionless datagram service, which means that no connection is established and packets may show up in any order. The data is sent in self-contained datagrams, which means the bytes from the application are merely encapsulated and just then sent to the IP layer. It doesn't offer any reliability in the service. In fact, it will provide no acknowledgements. There's a checksum to cover the header, but not the data. There's no mechanism to detect missing or missequenced data, and there's no flow control to prevent overrunning the receiver. So it's a very, very simple service. So why do we have it? UDP is used by applications that don't need reliable delivery, or applications that have their own special needs for retransmission and congestion control that they provide themselves at the application layer. So a good example is the DNS service, which is the domain name service for looking up names, returning an IP address based on a name lookup. That's a simple transaction. A packet is sent, a response is received. If it isn't received, then, well, it will just try again. There's no need for a complex byte delivery service. The UDP frame format is understandably very simple. Here is the UDP data that's been encapsulated inside the IP header, and we're looking at the UDP header over here. It just has the source port, the destination port. They are the same as in TCP. They just provide for demultiplexing the data to the correct application at the far end. The checksum is by default over the header. So it just calculates just checks that the UDP header is intact. Optionally, it can be used over the data as well, although that's not used very often. So in summary, TCP provides an in-order reliable delivery of a stream of bytes between application processes. This is the TCP service model. We saw a little bit about how it accomplishes that, and we're going to see more about how it does that later in the class. On the other hand, UDP provides a much simpler datagram delivery service. It's not reliable, doesn't promise to deliver the bytes in sequence, and so it merely takes the bytes from the application and tries to deliver them to the application process at the other end. This is the end of the video.